video is just to discuss in very general terms what goes on in a typical NMR experiment. We'll get more specific as we get to the different isotopes you're able to measure, but there are a few things that are all in common, and I thought it would be best to start at that point. The first important consideration to keep in mind is that this is a magnet experiment and you're looking at spectroscopy, which means energy changes. So the first thing you need isotopes or particles with a magnetic moment. Sometimes that's referred to as spin, although we can't really see particles spinning or not. They do create a magnetic moment as if they were spinning. Most of you are already familiar with electrons. Electrons, as you'll recall, have spin of 1/2. They're either with or against a field. And this was very important in considerations of bonding, because when two electrons form a bond, they need to be paired. And that is a concept that you've seen quite often. What you may not be aware of, but soon will be, is that many nuclei also have spin. It has no effect on the bonding, but it's this nuclear spin that has the consequences in NMR. Now, not everything has a nuclear magnetic moment. If the atomic number and the isotope weight are both even, then there's no magnetic moment. So carbon-12 has no magnetic moment because its number is 6 and its weight is 12. Oxygen-16 you can't do an NMR experiment on because its atomic number is 8 and its isotope weight is 16. But many others do. The most important isotopes for NMR, at least for us, is proton, which has a spin of 1/2. That means there are 2 magnetic spin states. Deuterium has a spin state of 1, which means it has actually 3 spin states, +1, 0, and -1. And that'll be important further down the line as you begin to understand more sophisticated experiments. Carbon-13, an isotope of carbon, has spin of 1/2. Nitrogen-15, a relatively rare isotope of nitrogen, has a spin of 1/2. And fluorine-19 is also at 1/2. And so you can do the NMR experiment with all of these isotopes and many more. The essence of the experiment is that you're going to place the sample in a magnetic field. The nuclei will align with respect to that field so that there is a net magnetic moment usually aligned with the field. The energy difference between the ground state and the excited state, that is, the moment aligned with the field versus aligned against the field, is very small, but the NMR experiment measures that difference by spectroscopy using radio frequencies to measure that energy gap. And so a little mock-up is, here is a spin 1/2 set of particles placed in a magnetic field. The normal way to denote a magnetic field is with beta. Different spins can align either with or against the field in your collection or ensembles of atoms that are in the magnetic field. This angle of about 45 degrees is intentional for quantum mechanical reasons, but if you take all of these vectors and add them up, in the ground state there is a net magnetic field response to the external field aligned with that field. And so the frequency you're measuring is the frequency at which the magnetic moment goes from with the field to against the field. What frequency is that going to be? That depends on how strong your magnet is. It depends on what specific isotope you're analyzing. Each isotope has its own magnetic field strength, and that term's often called the gyromagnetic ratio. When we talk about the strength of a magnet, we don't usually use the physicist term for magnet field strength, which is Tesla. We normally refer to the frequency at which the proton spin state change takes place. And those are typically in radio frequency in the megahertz range. So the NMR spectrometers at Miami include a 200 megahertz spectrometer, which is the one that's used in the undergraduate labs, a 300, there are two 500s, there are two 600s, and there's an 850. All of these instruments are made by the same company. They have the similar software, and so when you learn to run the 200, you know the basics of running the other experiments, although you get more sensitivity and can do more sophisticated experiments as the field strength goes up. So, the gyromagnetic ratio is going to determine the frequency of resonance. This frequency of resonance is called the Larmor frequency, and the higher the gyromagnetic ratio, the higher the frequency will be. This also determines the net size of the magnetic moment, which is really related to your signal strength. Also, when you're considering the strength of a signal in an NMR experiment, you need to consider the abundance of the isotope. So all of these things feed together to give you a field strength or a signal strength, and the signal strength is often very, very weak, and so you need to accumulate lots of scans and take care of the Felget advantage in order to actually see good spectra. Here's an example. If we look at proton, a Larmor frequency of a proton in a 400 megahertz spectrometer is 400 megahertz. It is nearly 100% abundance. There's only a little bit of deuterium in there, and the gyromagnetic ratio was 26.75. If we switch to deuterium, we see that deuterium is a much lower gyromagnetic ratio. It's a much lower abundance, and it is about 1/6 the resonating strength, resonating frequency in the same magnetic field. What does that mean? Well, what that means first off is that you're never going to accidentally be measuring deuterium signals in your proton area and for all the others. So each experiment is going to be specific to the isotope you're looking at. There's going to be no crosstalk between them in terms of gaining signals. The other thing is that the signal is going to be immensely weaker for the deuterium. You may need to enhance your deuterium, but even then, the basic field strength is only going to be less than 1/6 as large. If the strength of the signal is only 1/6 as large, you're going to need to use 36 times the number of scans to get equivalent signal to noise. And so that's a big barrier. Carbon-13 has a different gyromagnetic ratio. It's just about exactly 1/4 that of the proton, and it has a very small abundance as well. Most carbon is carbon-12. Nitrogen-15 is interesting in that it has a negative gyromagnetic ratio. That means that the ground state in nitrogen-15 is actually against the applied field rather than for the applied field, which is characteristic of all these other isotopes. And it has also a very small abundance. Nitrogen-15 is often very important for biological NMR, and so many protein structural studies will make use of nitrogen-15 labeled amino acids in order to get the data. Fluorine-19 is fairly common, and you can see that fluorine-19 is very close to where proton is, 376 megahertz, and fluorine-19 is 100% natural abundance. And so taking proton and fluorine spectra is relatively strong signals, easy to gather. You can actually do those in a single sweep. These others you have to accumulate spectra. So what happens as we look at spectra? Well, let's go back to electron for a second and see where that would stand on that same chart. The gyromagnetic ratio is about 70 times that of proton. It's incredibly sensitive to do electron magnetic resonance, but that's not generally much good in normal organic compounds because all the electrons are paired, so there's no magnetic moment. There is a technique called electron paramagnetic resonance, or EPR, sometimes called ESR, which is a technique that uses unpaired electrons. And when you have an unpaired electron, you can get very valuable and very sensitive information from it, but you need to take special measures to get a signal because you need unpaired electrons. Oftentimes that involves putting a functional group into your molecule that has what's called a spin label or an unpaired electron, or if you're doing organometallic chemistry, you use a metal that has an odd number of electrons so that there are leftover electrons in that way as well. So in the standard NMR experiment, if you think about it, at first glance, this is a useless technique. all of your isotopes are in one tube and it's stuck in the same magnet, shouldn't all protons resonate at exactly the same frequency? Shouldn't all carbon-13s resonate at their set frequency? If you think about that, then an NMR would just be a big isotope detector. Do I have protons or don't I, by seeing the frequency? But that's not the case because of a phenomenon called chemical shift. If all the atoms on an isotope were subjected to exactly the same magnetic field, then they would all resonate at the same frequency. But even though the sample is subjected to the same external field, the atoms and individual isotopes will have different frequencies due to shielding. The chemical environment, particularly electron density, will set up what's called a diamagnetic response. It will set up a field that opposes the applied field. That's called shielding, and it means that the magnetic field that the actual nucleus is subjected to is slightly smaller than the actual applied field. It's a very small effect. The effect's only a few hertz among many megahertz, but it can be measured and then interpreted in terms of the chemical environment of the protons or whatever isotopes you're looking at in there, and you can get chemical information based on these slight differences in frequencies. So in a typical experiment, the sample's dissolved in a deuterated solvent. Why a deuterated solvent? Because you're going to take lots and lots of scans, and you don't want your magnetic field to drift. And so you take the frequency of your deuterated solvent and lock that and use feedback electronics so that the magnetic field does not drift during the lifetime of the experiment, which in some cases could even be several days. You insert that sample in a deuterated solvent into a magnetic field, lock on that deuterium so it doesn't drift, and then you pulse that sample into its excited state and record the energy emissions. You do that for as many pulses as you need to accumulate a good signal, and then take a Fourier transform of those accumulated spectra, and that gives you the actual spectrum that you can interpret in the ones that we'll be looking at later. In future videos, we'll begin to start with basic NMR experiments and the information you can get. You're going to start with carbon-13. The reason to start with carbon-13 is not historical. Proton's much more sensitive, and so proton NMR predated C13 by quite a bit. But C13 is a little easier to interpret, and I think it's important for students to actually make use of information and see how this can be useful, and then go to increasing levels of sophistication on other experiments. By the time we reach the spring semester, we'll be on to far more sophisticated experiments, moving from what are called one-dimensional spectra to two-dimensional spectra, and you'll be able to solve tougher and tougher spectral problems by getting more and more information. And so that'll be something to look forward to, but at the moment we'll be concentrating on carbon-13 and moving from there.